Hello friends and welcome into yet another lecture on digital electronics and microprocessor. From previous two lectures we have started with the combinational circuit of encoders and decoders. In this connection only, in this lecture also, we are going to see the content of the different types of encoders, decoders, and the part of the arithmetic logic unit, which is the last content of this unit. In this lecture, we are going to see for binary to BCD converters. Then we are going to see for the arithmetic and logic unit also. The first topic we are starting today is BCD to binary converters. As we know that for any BCD number to be represented, only the decimal values from 0 to 9 are to be represented in form of BCD. And for every BCD number to be represented, a 4-bit code group is to be used. And that's why if I want to go for the representation of decimal numbers which are greater than 9, then similarly the next 4-bit groups also we have to use out, and that we are saying as a tens group, which is representing the MSB bit in BCD number and so on. That's why here when every BCD number we are observing and it is going to convert it into the binary, then the three basic steps we have to follow, and those three basic steps have been given over here. The value of each of the bit in the BCD number will be represented by the binary equivalent or the weight of that number. That means for BCD number, the LSB bit digit which is placed at the rightmost position will be having the weight which is indicated as 2 raised to 0. That means it is having a weight of 1's value. Then next to LSB bit will be having the weight of 2 raised to 1. That means it is having the weight of 2's. Next to the second bit after the LSB is having the weight or carrying the weight of 2 raised to 2, that is 4, and so on. That means as we are moving from left side to the right side, the weight of each of the bit in the BCD number is going to increase as a power value of that position for the base of 2. Then all the binary weights of the bits that are ones in the BCD are added. Once we have multiplied each of the BCD number by some 2's power value, we have to get those resultants to be added, and that will give you the BCD value. The result of this addition is the binary equivalent of any BCD number. The two-digit decimal values, which are ranging from 00 to 99, can be represented in BCD by using two 4-bit code groups. It indicates that every digit in decimal has to be taken individually, and for each individual digit corresponding binary representation of 4-bit group we have to represent. So let's see here 19. 19 is having units place value as 9 and tens place value as 1. So here 1 will be represented in binary form as 0001. 9 will be represented as 1001. But while placing these independent digit bits values, we have to place that as per their original number positions that we have indicated. That means 1 is placed at the leftmost, so corresponding bit group representation for 1 is placed on the left hand side, and on right hand side the 9th bit group representation has to be written. Now here that representation will give us equivalent binary value as 11001. This is the way how theoretically the BCD number has to be converted to binary number. So in this particular table, we are observing that for the BCD number, we are going to take the 5-bit representation. Why? Because the numbers greater than 9 also we have considered for representation in BCD. And as we have seen in this previous slide, for representing the number greater than 9, we will need the 5 number of bits. That's why here in this table we are using the 5 number of bit representation for the BCD value. From this BCD table or BCD column, you can observe that we are having the representations starting from 0. Then we have come to the maximum decimal number representation as a 9 in this BCD code conversion. Then after 9, here the MSB bit value will get indicated as 1, and again the equivalence of 0 to 9 values will be represented, because once we have reached to 0 to 9, here after that the MSB bit value will become 1. Again, by keeping that MSB bit constant, you are changing your values in LSB bit positions from 0 to next 9. In this way, when the next 9 will be reached, now in that case, here by using the 5 bits, the next representation of BCD code is not possible. So here by using 5 bits only, we can represent the BCD code values equivalent to the decimal value of 00219. And that's how here, after getting this BCD code to be written, the equivalent binary number conversion we have going to do. But while converting that into the binary also, as we are indicating this up to decimal 19, that's why in binary conversion also a group of 5 bit is necessary. And while converting this into binary, we are converting that by using the 2's power values, that is weight values multiplication to this binary representation, and their addition will be taken. So independently, just take one of the random example for checking these conversions to be obtained. So let's go for this row in which we are finding at 0th position value of bit is 0. So 2 raised to 0 into 0 is 0. Then 2 raised to 1 into 0 is again 0. 2 raised to 2 into 1, it makes the value as 4. And 2 raised to 3 into 1, that is 8 into 1 is 8. 8 plus 4 makes it 12. So I can say that this is a binary representation for the value of 12. This is how for any of the above or below row values you can get the conversion of decimal number into the binary number by the process of using the multiplication by the place weights to the given binary bit number. This is the way how we have obtained this binary number representation for given decimal number. After obtaining this truth table, the next thing what we are doing is writing the K-map corresponding to each and individual bit representation of the required type of code. And here required type of code is binary. And that's why for E, D, C, B and A, the separate truth tables we are going to write down from this obtained truth table. Now, in the K-map, we can see that as this particular truth table, we are going to write for 5 variables, and that's why here for 5 variables we are observing that the variables which are constant that we have written outside, and for that remaining 4 variables only we are writing the truth table. So this particular table is written for variable A. We have taken the variables for change as B3, B2, B1, B0 and B4 is 0. So 4 variable K-map we have presented. In the 4 variable K-map, you can observe here that for B4 is equal to 0, for A variable to be obtained, we have having the values which are of don't care for the highest mode bits and then for the previous values. Then after that we have seen that we are going to group for this 8 number of ones into the given K-map table. After that, here we are going to get the resultant of this K-map reduction as A equal to B0. Similarly, for B also, we are going to write the K-map from the inputs of these B4 up to B0. But again, in that situation, the B4 constant which is 0, that we are not going to consider for writing the K-map, and we are taking the other 4 variables from B0 up to B3. And we will map the values into the table for 4 variable K-map corresponding to this B4, corresponding to this B from the given truth table. So you can see here 0, 0, 1, 1 that has been mapped in first row. Then in the second row 0, 0, 1, 1 that has been mapped. Then in the third row, the values which we are going to consider will be 0, 0, 1, 1, then 0, 0 and 1, 1. So these things we are taking as a don't care conditions, because after the 8th value we are having this before we, as we are considered as a 0. So the next levels are taken to be don't care values. But in this case again we are finding out that 0, 0 has been mentioned for 8th and 9th, because we are knowing that our BCD numbers are extending up to 9th digit value. So again these 8th and 9th mean terms have been taken as 0, 0. After this, again, as per our rule, we are going to get the grouping of ones to be done along with the don't care condition. And by minimizing of this, we will finally find out the resultant which is given as this value which is indicated over here. Next, for the C bit, we are finding out the K-map reduction to be done out. And for that again, for the output variable of C, we are writing the K-map in the form of B1, B0, B2 and B3. Again we are considering the B4 value as 0, because here we are going to consider only the 0 to 9 values. But if you are observing, on the other side we have marked the condition of the truth table if we are going to take the B4 value consideration as 1. And for the B4 value consideration as 1, the next truth tables that we have indicated. So totally here we have marked out the 4 K maps corresponding to the condition of B4 value equal to 0, and in the next 4 truth table marking we have given B4 value is equal to 1, because B4 value will be 0 for only the decimal equivalent representation of 0 to 9, while B4 value will be 1 if the decimal numbers from 10 to 19 we are going to represent. And corresponding to that, the truth K map has been represented for A, B, C and D, and again for E variable in these two truth tables for each of the variable to be represented. So when B4 is 0, we are going to consider again the first 0 to 9 values. So 9 mean terms were there and other conditions will be taken as don't care, as we have done in previous all conditions also. Now corresponding to C, the initial values where B4 is 0, those 9 conditions we have to get mapped. Then for D also the same thing we are going to do, and here we are going to take the next table values where your B4 is 1, and in that condition whatever A, B, C, D, E is there, for that we are going to write the K map which is indicated on my left hand side of these all K map representation, and we have simplified those K maps. Finally, from those K maps, the result what we are getting is one and the same after getting the simplification of table to be done. And these equations of A, B, C, D and E we are going to represent in the form of a logical diagram. So you are observing here the 5 inputs which are indicated as B0 up to this B4, and here the 5 outputs in the form of A to E has been represented. The next is the reverse conversion, that is from binary to BCD. So binary numbers will be the weighted multiplication with bit value to represent any decimal, as we have seen in the previous case. So here the binary codes will be taken as a 4-bit representation only, because 4-bit binary representation is capable of giving the decimal equivalent representation up to 15 from the 0 decimal value. But to represent from the value of 10 up to 15 decimal in BCD, we will need the 5-bit group representation, and that's how here you are observing in the truth table in the BCD code column that after the 9 value, here the MSB bit has set to 1, and corresponding to the LSB digits of 0, 1, 2, 3, 4 and 5, the equivalent binary conversion has been done out in remaining 4-bit representation. So in binary code, the decimal value representation from 10 to 15 will be accommodated in 4-bit representation only, but BCD will take 5-bit representation for the same decimal numbers. After doing this all process, first simply we are going to write a mean term representation corresponding to each of the bit value. So let's start from this B0. So in B0 we are finding the first term, third term, fifth term, seventh, ninth, 11th, 13th and 15th term is present. That terms we have written out. That means which terms are as one value, those mean terms we are representing in this summation sign. Similarly, for B1, B2, B3 and B4, we are doing this operation to be repeated out. After doing this process, we are going for keeping the conditions constant for the given numbers. Now here the input variable is binary code. Binary code is having 4 input variables, so we have to write a K-map for 4 variables. And BCD code consists of 4 variable representation plus 1 extra bit representation of B4, and that's why here 5 separate K-maps corresponding to B4, B3, B2, B1 and B0 we have to give out over here. So here for B0, when we are writing the K-map according to this number presentation of the mean term representation, those terms only we are going to mark as a 1. After doing the marking, then K-map simplification by grouping ones you have to do, and this K-map simplification will result into the value of A. In the same way for B1 you are going to write a table. In that table, again by using this mean term equation representation, we have mapped the values of ones and zeros into the given table, and the simplification will be obtained as DCB dash plus D dash B after getting this grouping of 4 ones and 2 ones that has been made up. Then next we are writing the K-map for this B2. For that, this third mean term equation we are going to use, which is indicating that 4 up to 7 terms are 1, and again after that 14th and 15th term is 1. So this will be marked down. For getting simplification, grouping of these first 4 ones will be done, and another 4 ones will be grouped out by making this group possible, and its simplification will give us result as D dash C plus CB. Next, K-map will be written for B2 variable. In the B2 variable, we are observing that only 8th and 9th term is present, so that terms will be indicated as 1 and all other terms are 0. Then simply pair of these ones will be formed, and the resultant what we are obtaining is DC dash B dash. Finally, for B3 we will write, B4 we will write a truth table. In that we are having presence of the mean terms which are starting from 10 to 15. So those mean terms that we have indicated as ones over here. Again these 4 ones will be obtained. Then a quad of these ones will be formed out, and resultant will be DC plus CB. Now by using these all logical expressions, we are going to have a diagram to be plotted on this side. But if you are observing, we will need for each variable the complemented form also. So we are getting the complements to be done with this inverter gate, and here we are observing that addition, that is ORing of the ANDed variables are there, and that's why here first level will be obtained by the ANDing gate implementation, and next level will be obtained by giving the ORing of the variables, which is of obtained by doing the ANDing operations. And this is how here for these converters the first level implementation is of ANDing and second level implementation is of ORing operators. And for ANDing operator input, either the original input variable or the complemented input variable will be provided. The next topic we are starting is encoder, and encoder is exactly reverse to the decoder operators. That means in the decoders we are having the n number of inputs and m number of outputs, but always in the decoders, number of input lines were more as compared to the output lines. While in case of encoder, the number of input lines will be more, but the number of input lines will be less as compared to the input line. So the combinational circuit which is performing the inverse operation of decoder is said to be encoder. And as I have said, there will be also n number of input lines for this encoder and m number of output lines for this encoder. But as I have mentioned earlier, for the encoder, this output number of lines will be always less as compared to the input number of lines, because in encoder the input value is going to get encoded. Encoded means in minimum number of bit representation or in minimum number of output line representation. So this encoder produces always the m-bit binary code, and that m-bit binary code corresponds to the digital input number. So always on the input side also we are having digital inputs, and on the output side also the digital output we are going to obtain. And this particular encoder is going to accept the n input digital word and converts it into m bit another digital word. So as I have mentioned, both input and output will be in the form of n bits only. In digital word form only. Only the grouping of bits will be with n and m words in such a way that m is always less than n. So here let's see that the problem statement of conversion or designing the encoder which is going to convert from decimal to BCD. So to convert any decimal number into BCD number, we have said that we will require the 4-bit binary code representation, and that's why here for this encoder we will need the 4 lines of outputs, while we are going to take the decimal number as an input and maximum decimal number representation in one digit representation are from 0 to 9. So 10 different values we are giving at the input side of this encoder. So this decimal to BCD encoder is coming out as 10^4 encoder also, which is having 10 inputs and 4 outputs. Now corresponding to this equivalent writing of the decimal number in the truth table, as we are wanting the BCD encoder to be obtained, so the output variables will be these BCD variables, that is A, B, C and D. Now in this A, B, C, D we have to mark out which mean terms are to be present, and based on every individual column consideration, this mean term equations we are going to write down. So in the mean term equations you can observe here for A, 8th and 9th term value are only 1. So here we have written this mean term representation with 8 and 9 term present. Then 4 to 7th term are present for B value. So mean term representation is having 4 to 7 terms. For C, second, third, 6th and 7th term are present. So it is presented. And for D, all the odd terms are present. So it has been indicated over here. Once this mean term has been represented, then the next step is we have to go for representing the K-map of these for individually to be written for A, B, C and D by using this K-map representation. And please remember friends that here we are writing the K-map for the variables which are indicated for the mean terms of 8 and 9. But if you are observing in the truth table, we are having only one input at a time. And that's why here, if you are observing, when the mean term of 8 and 9 is taken, at that time, for A to be obtained, the 8th and 9th input we have connected over here, and it is a mean term representation, so we are going to OR those terms over here. Then the next case is of 4th, 5th, 6th and 7th mean term to be obtained. That's why for B to be obtained, we are having the inputs which are coming. Let's follow the pointer over here. So this is your 4th input. Then this is a 5th input. Then this is a 6th input and this is a 7th input. So the corresponding from this mean term, these variables will be taken from the input which have been marked from 0 to 9 and ORing of them will be done, and finally the required variable is obtained as per these mean terms that we have written. Here for the K-map, we are having only one input, and that's why writing K-map is not suggested for this particular diagram implementation. Rather than that, directly from the given inputs, the ORing gate output formation that we are going to do out. Then next case is of octal to binary encoder. And this octal to binary encoder we are going to do with the help of again the number of bit group representation. When we are doing this conversion from octal to binary, at that time we have to remember that as it is octal to binary, so it will have 8 inputs, one for each of the octal digit, and it will have 3 outputs which will generate the corresponding binary number. And that's why here we are observing in this truth table that there will be totally 8 octal numbers 1, 2, 3, 4, 5, 6, 7 and 8, in which at a single time only one digit of octal will be made 1 while all other digits in that number will be kept as 0. So we are starting from this LSB bit to be 1 because this is D0 indication. Then we are moving further with each of the digit to be made 1 at every next time, and finally D7 bit has become as 1. And we are converting this representation into equivalent binary representation. So when my MSB bit will be 1, it is considered that the representation of 8 will be there. But 8 we are indicating from 0 to 7 higher level representation. So it is equivalent representation of 7. While D0 is 1, it will be taken as the binary representation of 000. and so on. So this D1 is 1, so one input is present, so equivalent representation of binary as 001 that we have represented. Now, in this case, you are observing again that the encoder what we are going to obtain for octal to binary is having 8 number of inputs. So, the 8 lines have been represented on the input side and it is converted into binary, and for binary conversion from 0 to 7 value of decimal, you will need maximum of 3 number of bits. So 3 output lines of ABC has been represented. So octal to binary encoder will be also said to be 8:3 encoder. Now, in the same way what we have done in previous case, we will write the values of mean term representation for each of the output variable of A, B and C. And that A will observe the presence of ones for 4th up to 7th mean term. So here 4 to 7 we have mentioned. For B, 2nd, 3rd, 6th, 7th term are present. For C, 1st, 3rd, 5th and 7th term is present that we have represented. Now after doing this, as our inputs are 7, that's why here vertically the 7 lines of inputs we will place, and for formation of ABC 3 outputs we are going to take ORing of the input variables which are indicated in each of the separate corresponding mean term representation. This is how here we will find out this ORing of gates have been done from corresponding inputs that we have presented in the mean term representation. But friends, please remember that when we are indicating such like encoder, at that time we may face two different problems. And those two problems will be stated over here on this slide. In this case, you can see that in the table, at every time only one bit is made to be 1 to indicate that particular line is going to be high and all other lines are 0. But if suppose we are finding a random case of D3 and D6 bit both are 1 at the same time, then this encoder will generate the output of 111. This does not represent that either D6 or D3 is 1. Sorry. To resolve this problem, the encoder circuit must establish an input priority to ensure that only one input is to be encoded. That means I am making D3 and D6 both as 1. So, for the output generation, it will not be clear that whether corresponding to this D3 bit 1, the output to be generated as 011, or with D6 value to be 1, it has to generate the output as 110. It will not made clear, and that's why it will generate any random output which is 111. So friends, please remember that if such like case is there, simply implementation of encoder is not sufficient, but instead of that, the priority encoder we have to define, wherein there will be one extra input of priority has to be presented, and that input when made 1 according to this priority which is assigned either to D6 or D3, corresponding output has to be get generated from the encoder output. And if such priority we are assigning as per the highest priority provided number, the corresponding output will get generated. The second problem which may arise in the encoders is corresponding to zeros values. Here we have seen that if simultaneously any two digit values are made as 1, then an output with all zeros is going to get generated when all the inputs are 0. So let's check out for this. So here output for all the bits is generated as 0 only when all the bits are going to be 0. Here that case we have not represented in the particular truth table, but we have presented the case of when D0 is 1 and all other inputs are 0, that time also all the outputs are 0. So now you might have understood the discrepancy that when all the inputs including D0 are 0, that time also ABC output will be 0, and at the same time when D0 is 1 and all the other inputs are 0, that time also output generated is 0. So how to understand whether that output is corresponding to all 0 inputs or D0 is 1 and all other inputs are 0. And to get this discrepancy to be resolved, we have to provide one more output to indicate that at least one input is equal to 1. And that's why to solve these two problems, the next type of encoder which is mentioned is priority encoder. But friends, today we are stopping over here with these two encoders only, and in next lecture we will go for the priority encoder and the design of the combinational circuits by using the mux block representation. So we are going to stop over here today.